All right, let's get straight into it. This is your rapid revision explainer for AQA Chemistry, and today we're diving into section 4.103, using materials. We're going to cover everything you need to know about why we pick certain materials for certain jobs, so let's do this.
So, to kick things off, here's a question for you. Why is it that a steel car will start to bubble up with rust after a few years, but you can see an aluminum drinks can sitting by the road for decades and, well, it looks basically fine? The answer is all about how materials react with the world around them, a problem chemists are always trying to solve.
And that leads us perfectly into our first big topic, the constant battle against materials breaking down. We're talking about corrosion, and of course the most famous example of them all, rusting.
So what exactly is corrosion? Well, simply put, it's when a material gets destroyed because of chemical reactions with its surroundings. It's less of a flaw and more like nature just trying to turn those refined metals back into their more stable, original forms. Okay, this is a classic exam question, so listen up. What do you need to make rust? It's a pretty simple recipe, but you absolutely need two key ingredients. Of course you need iron, but, and this is the bit everyone forgets, you need both oxygen and water. If you take away just one of those, the iron won't rust. And the result? That flaky brown stuff we call rust. Or if you want to be fancy, hydrated iron 3 oxide. Right, so if we know oxygen and water are the culprits, the easiest solution is just to keep them out, right? The first line of defense is a physical barrier. Think about it, painting a garden gate, putting grease on a bike chain, or electroplating a shiny tap. All these things just put a protective layer between the metal and the air. Simple, but it works.
But what happens if that barrier, that paint, gets scratched? Now we need something a little bit cleverer. Sacrificial protection. Instead of just a simple barrier, what you do is coat the iron with a more reactive metal, like zinc. So if that coating gets damaged, the zinc will react with the air and water instead of the iron. It basically takes the hit, sacrificing itself to keep the iron safe. Pretty smart, huh?
Okay, so that's how we protect metals. But what if we could just build stronger materials from the get-go? Well, this is where alloys come into the picture. Turns out, pure metals are often way too soft for most jobs, and alloys are the engineered solution. But why is that? If pure metals have these beautiful, simple, regular structures, why are they so often, well, kind of useless? The answer, funnily enough, is because of how regular they are. And this explains it perfectly. In a pure metal, all the atoms are the same size, and they line up in these neat, tidy layers. Think of them like a stack of playing cards. They just slip and slide over each other really easily. That's what makes the metal soft. But with an alloy, we mix in atoms of different elements, which are different sizes. These new atoms completely mess up the neat layers, distorting them. It makes it so much harder for the layers to slide, and bam, the alloy is way harder and stronger.
Here is your quick fire guide to the alloys you absolutely have to know for your exam. First, you've got bronze and brass. They're both based on copper, but bronze is mixed with tin and brass with zinc. Then you have the steels, alloys of iron and carbon. High carbon steel is super strong but brittle, great for tools. Low carbon steel is softer, so it's perfect for things like car bodies. And finally, stainless steel. We add chromium and nickel to the iron, which makes it hard and, crucially, stops it from corroding. Perfect for your cutlery.
And hey, this isn't just about industrial stuff. It's in your jewelry box, too. Pure gold, which is 24 karat, is actually really, really soft. So for jewelry, we almost always use an alloy. 18 karat gold, for instance, is only 75% gold. The rest is mixed with metals like copper and silver to make it much harder and more durable.
Okay, let's move on to our final section. We're now looking at materials that are often designed from the ground up for very specific purposes. We're talking about ceramics, polymers, and composites. First up, ceramics. You probably know these. They're typically hard, brittle, and brilliant at resisting heat. We're talking about your classic pottery and bricks, which are made by firing clay. But it also includes glass. Most of the glass around us is soda lime glass, which is just made by heating up a mix of sand, sodium carbonate, and limestone.
Next up, polymers. The clue is in the name, really. Poly means many. Polymers are these incredibly long molecules that are made when you join lots and lots of small, identical molecules called monomers together in a chain. Honestly, just think of it like making a super long chain out of paper clips. Each paperclip is a monomer.
Now, this bit is absolutely vital. There are two main types of polymer, and it all comes down to their structure.
On one hand, you have thermo-softening polymers. These are just individual chains all tangled up, held together by weak forces. When you heat them up, those weak forces break, the chains can slide past each other, and the plastic melts. You can then reshape it. But on the other hand, you have thermosetting polymers. Here the chains are joined together by strong chemical bonds called crosslinks. These links are so strong they don't break when you heat them, so the polymer can't melt. It just gets super hot and eventually burns or chars.
And finally, we've got composites. You can think of these as material cocktails. They're made from two or more different substances that are combined to create a brand new material with better properties. You have a reinforcement, like fibers, stuck inside a matrix that holds it all together. The classic example is reinforced concrete. The steel bars are the reinforcement and the concrete is the matrix holding them. Right, that's the theory done. Let's finish up with the ultimate revision guide. These are the absolute must-know facts for your exam. Ready? Okay, rapid fire round. Let's lock this in. Rusting needs both air and water. Sacrificial protection uses a more reactive metal. Alloys are harder because different-sized atoms distort the layers. Thermosoftening polymers, weak forces between chains and they can be melted. Thermosetting polymers, strong crosslinks, they cannot be melted. Ceramics are hard and heat-resistant, and composites are a mix of reinforcement and a matrix. Got all that? Good. And to finish, here's a final thought. We've seen how we design materials for specific jobs, from stopping rust to making better tools. So the big question is, as we look to the future, what properties will our new materials need to solve massive challenges like climate change, space travel, or sustainable living? That's where all this science is heading. Okay, that's it from me. Good luck with your revision.